And she came into my office, she's a chemist. And she was going out on a cruise in early June and said, hey, is the lake overturned yet? I said, no, of course not, it's like early June. Could you check your website maybe? I go on, and indeed, the day she asked, one of these buoys reached that 4-degree mark. And it's just amazing that it would occur so early. And so here, so you can see that there are some years where in mid-August the lake still hadn't reached 4 degrees. So there's a huge amount of variability from year to year. But the trend is towards earlier overturn. Here's a picture of sort of a generic year at the surface of Lake Superior. This is at the central buoy, and any year we picked and any buoy would have looked roughly the same. We see this very slow warming until the buoy reaches 4 degrees Celsius, and the reason it's slow is that that heat that goes into the surface has to heat up the entire water column at that stage. So you're putting in sunlight, for instance, the major source of heat to the lake right now, and that has to heat up all 200 or 250 meters of water. So the warming is very slow. Once it reaches that 4-degree mark, you can start to form this layer of warm water at the surface. And so this is sort of the switch. This here is heating a pot of water for spaghetti on your stove, okay? And you put the pot of water on there, and you turn the burner on high, and maybe it takes 10, 15 minutes before it starts boiling. This right here is putting a kettle of water with a cup of water on the same burner, turning it to high. The same amount of heat goes in, but the temperature changes a lot faster because there's less water that you have to warm. So we see this rapid warming. We see maximum temperatures in the middle of August, perhaps, and then fall cooling here. We're here in early April, where it's still relatively cold. And then in this case, the buoy is recovering in November. And this is a comparison of 2 different years. 1998, a very strong El Nino year with a very, very early overturn, and 1996, one of the years that's sort of remarkable in the sense that we had a huge amount of ice cover the previous winter, had a very, very late overturn. And you see that changing the date of that overturn, in 1998, the lake simply had more time to get warm. So the summer temperature, it turns out, is a fairly strong function of when this overturn occurs. This begs the question, what sets the date of that overturn? Oh, and here are surface temperatures from 2010, incidentally. Is there any way we can focus this just a tiny bit?
Yeah.
It seems just a bit fuzzy from where I am.
Yeah.
Well, I don't think it's going to get much better. There it is. 2010, we set record warm temperatures. This is the central buoy. The red line is the surface temperature at that central buoy. The blue line is the average over the last 30 years. You can see that we were way above the average. And this gray hatching that I have here is the observed range of daily temperatures over the last 30 years. So we actually, for just a while, set record temperatures in the middle of August. Then we had some amazing wind events in the middle of August and the beginning of September that mixed a lot of that away. You can see the temperature dropping very rapidly during those days. I'm from California originally, and I had to be convinced. This is 2007. The last year we had really good ice in Duluth, and my wife's from Virginia, the state of Virginia, not the city, and our son. And we walked out here and we talked to the fishermen and stuff like that, and the ice was 10 inches thick. It's just amazing. And so what I want to talk a little bit about is the role that ice plays in setting up these cycles, okay, and setting that date. Ice is really interesting because when snow falls, you see these big white patches here and some ice ridges and stuff like that. Light colors are really good at reflecting sunlight, right? If it's a hot, sunny day, we like to wear light colors, unless we're sort of gothy or something like that. In which case, you see these people with black t-shirt, and you know they're roasting because that black color is really good at absorbing radiation, okay? We like to wear dark colors in the winter because we can absorb a little bit of what sunlight is available. So when ice forms on a lake, and especially once you get snow like this, sunlight that hits it just gets reflected back out into space in winter and early spring when the ice is there. Which means that sunlight radiation is not available for heating the lake. On the other hand, if we take that ice away, like what appears to be happening, ice levels have gone down. I'll show a slide here in a second. When those ice levels go down, more of that sort of winter and early spring radiation is able to be absorbed by the lake. And it results in a warmer lake in the winter, and you reach that overturn date earlier. So here's some pictures. This is the amount of ice cover on Lake Superior. Again, amazing amounts of fluctuation from year to year. From years like '98, where we had only a couple percent of the total coverage. This is a time and space averaged number here. And then other years like 96, I think that's this one right here, where we had, you know, the entire lake covered for about 40% of the season. So there's a lot of variation from year to year. But the trend is towards lower levels of ice. And so here are sort of the payoff slides. Oh, I should mention that this is not the only lake on which this is happening. This is from a wonderful paper by a guy named John Magnuson back in 2000. And there are records of ice on lots and lots of lakes and rivers. Ice, again, has a very strong cultural resonance, and people keep track of it. If you go up to Hibbing or something like that, and every little lake, they have a Chevy parked on it, and they have a pool about, you know, when the Chevy's going to fall through the ice, and people put money on various dates and stuff like that. This is a very strong tradition here. People are very interested in how long the ice is going to last. Okay, so there are records that go back. You see, these are all records that go back to 1845 here. Really amazing. And what you see in all of these is breakup dates getting earlier and formation dates getting later. Is the typical trend. In fact, I think there's one record here kept by Shinto priests on Lake Suwa that goes back to 1450. So really amazing records. But the point is that this trend for there to be less ice on lakes tends to be relatively global in scale. There was a wonderful paper by a high school student, Forrest Hauk, down in Bayfield, where he looked at the ferry schedule going out to Madeline Island, and the number of days per year that the ferry runs has increased because of there being less ice on the lake. So it's really very interesting. Oh, here it is. I have it right in. So here's the number of duration of closed navigation. So the number of closed days has gotten smaller and smaller from the mid 1800s through the present. An interesting sort of anecdotal piece of data. Okay, so here these are the payoff slides here. This is the amount of ice cover in the winter, and this is the date of the start of the stratified season. And what we see is when we have lots of ice cover, we have relatively late start of the stratified season, and when we have very little ice cover, we have relatively early start of the stratified season, as we would expect. And more importantly, here's ice cover on this axis, and here's summer water temperature on the y-axis. When we have lots of ice in the winter, we have a cold summer. And when we have very little ice in the winter, we have a warm summer. So it turns out that winter conditions in Lake Superior play a very important role in setting conditions in the lake even into the summer. It's a really interesting connection, and we think we've sort of established this stage. And then the length of that stratified season. This is from an analysis of that Sault Ste. Marie data that I started the talk with. We can look at when the season begins and ends, that stratified season, and it has become 22 days longer over the century. 22 days doesn't sound like a lot, but it's gone from about 150 days to about 170 days. That's an increase of about 15%. It's a really remarkable change in how the lake behaves, because the biology in the lake, or the ecology of the lake, is very different between the negatively stratified cold season and the warm season. So, you know, we're seeing this shift take place right now. Okay. So right now, what we have, the records I've shown you so far are temperature from the surface of the lake, taken from those NOAA buoys. I right now have funding from the National Science Foundation to put out this relatively large array of moorings. So we have moorings at 1, 2, 3, 4, 5, 6, 7 sites. I was at this DWI site. This mooring stands for Duluth Water Intake. And you see their depths here after them. So anywhere from about 100 meters to about 400 meters depth. And at each one of these sites, we have a big anchor and a cable, and we have temperature loggers clamped onto that cable at lots and lots and lots of different depths. So instead of just seeing what's going on right at the surface, we're seeing what the structure of the temperature is throughout the water. Here are some pictures from 2008, 2009 from 3 moorings. And you can see this is time on the x-axis and depth on the y-axis. You can see the summer stratified season at these 3 sites, and then that much deeper winter stratified season. And what's very interesting to us are things like, at the western mooring, the season is very long, but it's not that layer is not very deep. Whereas at the eastern site, it's a lot warmer, but that penetration is a lot deeper. And so what we're interested in is what gives rise to these sorts of spatial variations as well. Actually, you know what? There are a bunch of pictures here, but I think I'd rather show pictures from today. Oh, so this is another, let me just show you, so let me show you some slides from today, if that's okay.
Yeah.
I think that will be, and what I did here, I apologize for the sort of spontaneous nature of this, but
Change is constant.
yes. These are pictures taken, I wonder if there's a better way to do
I
this.
think if you double click, if you just, oh yeah.
I think if I go here and then I go to open with,
There's those. Yeah.
there we go. Today what we had, again, last week we realized we had an opportunity to get out this morning and get this meteorology buoy in the water. We decided that we would do that. These are pictures from somebody else's camera, and I'm going to click through them really fast because there's lots of them, but I'll stop on the ones where there's actually some content. So you can see us, we're here leaving Duluth. This is the Blue Heron, it's UMD's research vessel. I don't know if some of you have had an opportunity at one point around to see it. Here we are going under the bridge. Let's see if we can get forward to some science here. There are lots of ice out there today. It was really sort of cool. I'd never actually been out when there was lots of ice there, but it was just this grease ice right at the surface. Really pretty. Tourist stuff. So here's the deck of the buoy. You can see all the cables coming down, various sensors, getting everything set. There's a wind sensor here. We measure air temperature, relative humidity here. Radiation sensor there, and some solar panels here which keep it powered for the season. You can see here, this is a sunlight sensor. This senses infrared radiation, or radiation from atmospheric moisture, CO2. And so we're just heading out.
So this buoy is attached to the cable that also goes down?
So this buoy floats at the surface, obviously, since it does meteorology. And it has a cable with a bunch of thermistors all down the cable. So we get temperature in real time. In fact, I can give you a website today that has access to this buoy, so you can see the data coming in real time. As of this afternoon, I mean, this is new stuff. So just lots of pictures of getting everything set. Sharon Bowen from Sea Grant was out with us. Always happy to have her out there. This is this weird grease ice that was it's all sort of about a millimeter thick and just crackled through it. Ship out there. And we had to go all the way up to Two Harbors. He got to tour the engine room apparently. And then the buoy, the mooring that we had there had no surface expression. In other words, you could sail right over it, you would see nothing. And so what we do is we have what's called acoustic release, and we fire that release. It's sort of a claw that holds onto the anchor, and we can tell it to let go. And so we lose the anchors, which is not a big deal. And all the expensive stuff floats up to the surface. These are the surface floats that had just popped up to the surface. And then we steam over to them, and the technicians on the back, you can see them being pulled up with the crane right now, or winch, sorry. So here they're coming up. And here what you see is a temperature sensor. And this one actually senses pressure as well. And that we put in there in November, and every 10 minutes since November, it turns on, measures temperature, shuts itself back off. 10 minutes later, it does the exact same thing, over and over and over. And we had a bunch of these on the same cable, and I don't know whether there'll be pictures of more of them. I brought one along, just for fun. You can pass this around, or I'll pop this over. So this is what's on the cable, and just if you hold it up here and down here, not by the greasy part right in there, that's O-ring grease. It's not bad for you, but it's greasy. So here you can see they brought those floats up onto the deck at this stage, and they're pulling more cable in, and they pull the instruments off. And at this stage, we're turning the boat around, and we're getting ready to put the meteorology buoy back in the same place. These are day shapes that tell other boats around us that we are currently disabled, and we have lines over the side